Gears play an important role in mechanical engineering. They are used in gearboxes, for example, to transmit and convert torques. The shape of the teeth has a decisive influence on the power transmission. The tooth shape used is a so-called involute. The use of involute gears is due to the favorable meshing and the fact that they are relatively simple and therefore inexpensive to manufacture. To understand why the involute is particularly suitable for the tooth shape, you first need to understand how it is constructed. The construction of an involute, or more precisely the involute of a circle, is therefore explained in more detail in the following. To construct the involute, imagine a disc. This forms the so-called base circle. We now wrap a thread around this base circle or disc. Attach the tip of a pencil to one end of the thread. Now unwind the thread from the disc and keep it taut. The pencil now draws the circle's involute. Two mirror image involutes then form the shape of a tooth. The gear is then cut out slightly below the base circle to allow the teeth to engage. In this area below the base circle, the teeth of the gears do not touch anyway. This so-called tooth root therefore has no significance for power transmission. The exact geometry of the tooth root therefore plays a minor role. The construction of the involute can also be imagined as rolling a straight line on the base circle. The trajectory of the rolling straight line then describes the involute. For this, again imagine a disc that forms the base circle. We now place a ruler on this disc with its origin at the highest point of the disc. The ruler forms the so-called rolling straight line. We place the pencil at the 0 point of the ruler. Then roll the ruler along the disc without sliding. The pencil now draws the involute. Note, an involute of a circle is created by rolling a straight line on a base circle. The resulting trajectory describes the shape of the involute. If the involute is constructed with a rolling straight line, it becomes particularly clear that the longer the involute, the less it is curved. In this case, the radius of curvature of the involute is 3 centimeters. The radius of curvature is the distance between the point of interest on the involute and the point where the straight line touches the base circle. In principle, this is the same as the arc length on the base circle, since the straight line is rolled on the base circle without sliding. This fact will become relevant later with the so-called base pitch or meshing pitch. If we now roll the ruler further and draw the involute a little longer, the radius of curvature increases. At the considered point, the radius of curvature of the involute is already 6 centimeters. The involute is therefore less curved at this point than at the previous point. So note, the longer the involute, the less it curves. This is used, for example, in profile-shifted involute gears, where the tooth profile is made from the part of the involute that is further out. The illustration shows the red profile-shifted gear in comparison to the blue non-profile-shifted gear. Although it has the same number of teeth, the involute is slightly longer. The teeth are then less curved in this region. When in contact with another gear, the contact force is therefore distributed over a larger area. This reduces tooth loading and therefore tooth wear. We will look at profile shifting in more detail in another video. But note, profile-shifted gears use the less strongly curved part of the involute for power transmission. In the following, we will take a closer look at the nomenclature used to describe gears. We have already seen the importance of the base circle in the construction of the involute. The size of a gear is described by the so-called standard reference pitch circle diameter. On this pitch circle, the circular tooth thickness and tooth space width are equal. However, this only applies to non-profile shifted gears. We will go into the importance of the pitch circle in more detail in a moment. The upper part of a tooth up to the reference pitch circle is called the addendum, the lower part the addendum. To avoid contact between the tip and root of two meshing gears, the root of the tooth is rounded. This fillet forms the root of the tooth, also called the bottom land. The diameter of the addendum circle is called the root diameter, and the diameter of the addendum circle is called the tip diameter. The power transmitting part of the addendum, where the teeth of two gears touch, is called the face of the gear. The force transmitting part of the addendum is referred to as the flank. This flank ranges from the reference pitch circle to the base circle. Note that within the base circle there is no contact and therefore no power transmission between the teeth of two meshing gears. An involute cannot be constructed within the base circle anyway, as an involute only exists outside the base circle. It should also be noted that the root circle does not always have to be smaller than the base circle. Especially for gears with a large number of teeth, the root circle diameter may well be larger than the base circle diameter. Let us take a quick look at the significance of the reference pitch circle. The reference pitch circle is called as such because the pitch of the teeth is referenced on the basis of this circle. This circumferential pitch, also called circular pitch, is the distance between two faces or flanks of the same direction on the pitch circle and thus corresponds to the sum of the tooth space width and the tooth thickness. This circumferential pitch must be the same for all gears so that the teeth can mesh without interfering with each other. In principle, the pitch of the teeth can be specified not only based on the pitch circle, but also based on the base circle. In this case, the pitch is referred to as the base pitch or meshing pitch. More on this later. In simple terms, the reference pitch circle diameter corresponds to the diameters of imaginary cylinders, called pitch cylinders, rolling on top of each other without sliding. The reference pitch circle diameter represents the size of a gear, so to speak. The exact definition of the pitch diameter will be discussed later. One of the most important parameters used to characterize gears, and in particular to ensure that the teeth of two gears can mesh with each other, is the module M, also called modulus. The module is a measure of the tooth size of a gear and is given in millimeters. Only if the teeth of gears have the same size, and therefore the same module, can they mesh. The module corresponds directly to the addendum HA of the tooth. As the tip of the tooth engages with the mating gear below the pitch circle, the addendum of the tooth HD must also be at least equal to the module. However, a clearance C is also taken into account in order to avoid contact between the top land and the bottom land of the meshing teeth in any case. Depending on the application, the clearance is typically 10 to 30% of the module. The factor 1/6, that is 0.167, is often chosen. The total tooth height H results from the sum of the addendum HD and addendum HA and therefore corresponds to twice the module M plus the clearance C. So note, the module is a measure of the tooth size. The larger the module, the larger the tooth. Only gears with the same module can mesh with each other. Let's take a closer look at the standard reference pitch circle. If we ignore the clearance, the tooth is divided by the reference pitch circle at half height, so to speak. The standard reference pitch circle diameter can therefore be defined as the diameter of a circle that divides the teeth at exactly half their height, without taking the clearance into account. The reference pitch circle diameter D0 is directly related to the module via the number of teeth. The standard pitch diameter D0 results from the product of the module M and the number of teeth Z, and as already mentioned, is a measure of the size of a gear. The reference pitch diameter is therefore a fixed parameter of a gear and serves merely as a reference circle, so to speak, which not only divides the teeth at half height, but to which the circumferential pitch P0 of the teeth is also related. As already mentioned, this tooth spacing on the reference pitch circle must be identical for all gears so that the teeth can mesh without interfering with each other. The circular pitch P0 can be determined from the quotient of the pitch circle circumference U0 and the number of teeth Z. We express the pitch circle circumference here as the product of the pitch circle diameter D0 and the number pi. The pitch circle diameter can in turn be written as the product of the module and the number of teeth. We can now cancel the number of teeth and obtain the circumferential pitch P0 from the product of the number pi and the module M. At this point it becomes clear once again that only gears with the same module can be paired, as only then will the tooth distance P0 be the same for all gears and the teeth can mesh. Note that reference pitch diameter and module are directly related by the number of teeth. However, both variables have their own meaning for gears. While the module describes the size of a single tooth, the reference pitch diameter describes the size of the entire gear. It should be noted that the module, like the circumferential pitch, basically indicates a pitch. To determine the circumferential pitch, the circumference of the reference pitch circle is divided by the number of teeth, while to determine the module, the diameter of the reference pitch circle is divided by the number of teeth. Just as the circumference of a circle and its diameter are related via the number pi, the circumferential pitch is related via the number pi to the module. A module of 8, for example, means that there is one tooth on the circumference for every 8 millimeters of gear diameter. Be careful at this point. Although the term diametral pitch could very well be used instead of the term module, this term is already defined differently. The diametral pitch dP is the inverse of the module M. The term diametral pitch is therefore somewhat confusing, because unlike the base pitch or the circular pitch, the diametral pitch doesn't indicate a distance per tooth, but the opposite, teeth per distance. To be consistent, the module M should actually be the real diametral pitch. This inconsistency is the reason why we don't use the term diametral pitch in this video to characterize gears, but only the module. Let us now determine the circular tooth thickness S0 and the tooth space width E0 on the reference pitch circle. As already mentioned, for gears without a profile shift, the tooth thickness S0 and the tooth space width E0 are equal to half the circular pitch P0, which can be obtained from the product of the module M and the number pi. The formula shown therefore applies to the calculation of the circular tooth thickness and the tooth space width. Since the tooth space width and tooth thickness are the same, the tooth of one gear fits perfectly into the tooth space of the other gear. The gears can therefore mesh without backlash. This means that there is no rattling when the direction of rotation is changed. The pitch circle diameter D0 can now be used to determine the tip diameter dA and the root diameter dd. The tip diameter results from the reference pitch circle diameter D0 plus the addendum on either side of the circle, where the addendum is directly equal to the module. The tip diameter can therefore be calculated from the module and the number of teeth as shown. The root diameter dd is obtained from the reference pitch circle diameter D0 minus twice the addendum. If we express the addendum by the module and the clearance, we obtain the given formula for determining the root diameter. The last parameter to be determined is the center distance between two meshing gears without profile shift. This distance without backlash is also called the standard center distance A0. The standard center distance is the sum of the two standard reference pitch circle radii, or half the sum of the pitch circle diameters, as the pitch circles are imaginary cylinders that just touch each other. If the pitch circle diameters are expressed as the product of the module and the number of teeth, the following formula is obtained for calculating the standard center distance. For gears without profile shift, almost all relevant geometric parameters are now determined. The calculation of the base circle to determine the involute tooth shape will be discussed in more detail later. To better illustrate the different meanings of module and reference pitch circle, the figure shows gears with different modules but identical reference pitch circle diameters. As already explained in somewhat simplified form, we have equated the reference pitch circle of two meshing gears with imaginary cylinders, called pitch cylinders, that roll on each other without sliding, so that the circumferential speeds on the pitch circles of both gears are the same. The point at which the pitch cylinders touch is referred to as pitch point C. However, the statement that the reference pitch circle diameter is actually identical to the diameter of the pitch cylinders is only true if the center distance of the two gears is equal to the standard center distance, and the gears therefore mesh without backlash. As the center distance is increased, the pitch circles where the circumferential speeds are the same also increase. In addition, the gears no longer mesh without backlash. Therefore, a distinction must be made between the operating pitch circle and the reference pitch circle. The dashed lines show the reference pitch circles and, in comparison, the operating pitch circles as black continuous lines. The reference pitch circle is a fixed parameter of a gear and only describes its size. The reference pitch circle diameter results from the product of the module and the number of teeth and is independent of the center distance. The operating pitch circle, on the other hand, describes the diameter of an imaginary cylinder on which the circumferential speed in mesh is equal to that of the mating gear. This operating pitch circle is indeed dependent on the center distance. So note, the reference and operating pitch circles of a gear are only the same when the gears are paired with the standard center distance. As already explained, the modules must match for the teeth of the gears to mesh without interference. However, it is not only the tooth size that is decisive, the shape of the teeth must also match. The shape is basically an involute, but depending on which base circle diameter is used for the design, a different section of the involute is used as the tooth profile. The image shows gears that all have the same module of 5, the same number of teeth of 16, and therefore also the same reference pitch circle diameter of 80 mm. The other parameters we have learnt so far, such as circular pitch, tooth thickness, and tooth space width on the reference pitch circle, are also the same for all three gears. Moreover, all teeth have an involute shape. Nevertheless, there are clear differences in the tooth shape, which lead to an interference of the teeth in mesh. The different tooth shape is due to the fact that the involute gears were designed with different base circle diameters. A base circle diameter of 75 mm was used for the first gear, a smaller diameter of only 69 mm for the second, and a larger base circle diameter of 79 mm was used for the third gear. We can see from these examples that when larger base circle diameters are used to construct the teeth, the teeth tend to look square. If, on the other hand, smaller base circle diameters are used, the teeth tend to be pointed. Let's start with some basic facts about the properties of involutes. The shape of an involute, and therefore the shape of the tooth, depends only on the diameter of the base circle. Each base circle therefore results in a specific involute. However, all involutes are geometrically similar. This means that they can be brought to the same shape by simply scaling them up or down. Let's take a look at the base circle marked in red and the corresponding involute. Now we rotate this base circle and align the center with the center of the gear with the larger base circle. We then scale up the base circle with the respective involute. We can see that this gives us the same involute shape. We can also place this base circle in the center of the right gear. If we reduce the base circle with the respective involute, we also get the same involute shape. All involutes are therefore geometrically similar regardless of the diameter of the base circle. Therefore, identical tooth shapes would only result in this case if the same base circle diameter had been used to design the tooth profile for all three gears. However, it makes little sense to specify a certain base circle diameter for gears, since this would only apply to a specific reference pitch circle diameter, and therefore only to a specific number of teeth. If the number of teeth of a gear and therefore the reference pitch diameter increases, a larger base circle diameter must of course also be used for the design of the involute tooth. Due to the geometric similarity of involutes just explained, in this case the base circle diameter must increase to the same extent as the reference pitch circle diameter in order to obtain geometrically similar teeth. It should be noted that the term similar is to be understood here in the mathematical sense, and not in the everyday meaning of approximately. To ensure that the tooth shape is always the same regardless of the size of the gear and that the teeth can mesh properly, the base circle diameter dB must always be in a certain constant ratio to the pitch circle diameter d0. The determination of this constant ratio is discussed in more detail in the following. The ratio of the base circle diameter to the reference pitch circle diameter is obtained by pairing two non-profile shifted gears without backlash. The center distance is then equal to the standard center distance A0, and the reference pitch circles of the two gears just touch at the pitch point C. If you now create a tangent to the two base circles of the gears, this forms the so-called line of action. Not only does the pitch point C lie on this line, but the power transmitting faces of the gears are also in contact with each other on this line. In principle, this is the straight line with which the involute tooth shape was constructed. This now results in the point of contact of the teeth always being on this line during meshing. We will go into the meshing itself in more detail in another video. This line of action now forms an angle with the normal of the center line. This angle is called the standard pressure angle alpha 0. As shown by the red and blue triangles in the figure, the base circle radii RB and the reference circle radii R0 are related by the standard pressure angle alpha 0. Of course, this also applies to the corresponding diameters. The cosine of the standard pressure angle corresponds to the quotient of the base circle diameter and the reference pitch circle diameter. In practice, the constant diameter ratio of the base circle and pitch circle, and therefore the involute tooth shape, is determined using this standard pressure angle. Independent of the module, a standard pressure angle of alpha 0 equals 20 degrees is usually used for gears. However, there are also gears with a standard pressure angle of 14.5 degrees or 25 degrees. In the case considered before, a standard pressure angle of 10 degrees was chosen for the left gear. The right-hand gear has a standard pressure angle of 30 degrees, and the gear shown in the middle has a standard pressure angle of 20 degrees. The fact that the standard pressure angle directly determines the tooth shape of a gear is also immediately apparent for manufacturing reasons. This is because gears are usually manufactured by hobbing. In this case, the tooth shape is determined by the inclination of the cutting edges of the rack-shaped tool profile. This tool angle corresponds directly to the standard pressure angle alpha 0. The relatively simple and cost-effective production of involute gears now also becomes clear. This is because no complex tool geometries are required for this, only tool cutting edges with straight geometries. At this point, let's summarize the most important parameters of a gear. The reference pitch circle diameter D0 is a measure of the size of an entire gear. The module M, on the other hand, is a measure of the size of an individual tooth of the gear. However, both variables do not yet determine the tooth shape. This is determined by the standard pressure angle alpha 0. By solving the respective formula, we obtain the required base circle diameter for the construction of the involute tooth for each reference pitch circle diameter. Since the diameter of the base circle is known, the pitch of the teeth can be related not only to the pitch circle, but now also to this base circle. This is referred to as the base pitch PB. Since the base circle diameter is obviously smaller than the pitch circle diameter by the factor cosine alpha 0, the pitch on the base circle is also smaller by this factor. The formula shown therefore applies to the pitch of the teeth on the base circle. At first glance, the indication of the base pitch PB in addition to the circular pitch P0 may seem somewhat unnecessary. However, the pitch on the base circle has a further significance for the meshing properties of involute gears. Due to the special design, all involutes of a gear are basically equidistant from each other, which means that the right-angle distance between two neighboring involutes is the same at all points. This distance between adjacent tooth faces is equal to the base pitch because the involutes are constructed by rolling a straight line on the base circle. To illustrate this, let us look again at the construction of the involute by rolling a ruler on the base circle. The base pitch PB is shown. If we now roll the ruler without sliding, it becomes immediately clear that the base pitch corresponds to the distance between two involutes. As all involutes are equidistant from each other, this is also true if we roll the ruler further. Let us now bring a second gear in contact with this gear without backlash. It then becomes clear that the base pitch corresponds to the distance between the power transmitting teeth during meshing. The base pitch is therefore also referred to as the meshing pitch. The meshing takes place on this contact line, which ultimately corresponds to the tangent to the base circles of the gears. This is the line of action already explained. Due to its complexity, we will take a closer look at meshing in another video.